The morning of February 25, 1945, a Vought F4U-1D Corsair came down hard in a rice paddy near Tsuchiura City, roughly 40 miles northeast of Tokyo. The pilot, suffering from battle damage and critically low on fuel, had no choice but to make an emergency landing in enemy territory. Within hours, Japanese Army technical personnel arrived at the crash site. The aircraft was surprisingly intact. The bent gull wings that gave the Corsair its distinctive profile were crumpled but not destroyed. The fuselage had buckled on impact but remained structurally sound. And most importantly, the massive Pratt and Whitney R2800 double Wasp engine, all 18 cylinders of American radial power, sat embedded in Japanese soil, waiting to be examined. What the Japanese engineers discovered when they began their analysis would fundamentally challenge everything their nation's aviation industry believed about engine design, manufacturing capability, and the vast industrial chasm separating Japan from the United States. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This wasn't just another captured enemy aircraft to be catalogued and studied. This was physical evidence of an engineering achievement that Japanese manufacturers, despite decades of aircraft development, could not replicate. The R2800 represented a level of power output, manufacturing precision, and metallurgical sophistication that exposed uncomfortable truths about Japan's industrial limitations in the face of American mass production. The Corsair had been shot down during the escalating American carrier raids against the Japanese home islands. These raids, growing in intensity throughout early 1945, brought waves of American fighters and bombers within striking distance of Japan's most critical industrial targets. The Japanese had captured enemy aircraft before. Zeros had forced down B-17 flying fortresses. Army units had retrieved crashed P-38 Lightnings and P-51 Mustangs from battlefields across the Pacific. Each captured aircraft was meticulously documented, photographed, and when possible, test-flown to understand American tactical advantages. But the examination of power plants told a different story than airframe analysis. When Japanese engineers studied captured engines, they weren't just learning about enemy capabilities, they were confronting the fundamental limitations of their own industrial base. And the R2800, with its extraordinary power output compressed into a remarkably compact package, would prove to be the most sobering revelation yet. February 1945 found Japan's aviation industry in a state of desperate innovation, tempered by crushing material realities. The Nakajima Aircraft Company and Mitsubishi Heavy Industries, Japan's two largest aviation manufacturers, had been producing aircraft and engines since the 1920s. These weren't inexperienced manufacturers stumbling through wartime production. Nakajima had been building aircraft since 1918. Mitsubishi's heavy industry pedigree stretched back to the late 1800s. Both companies had licensed foreign engine designs, studied Western manufacturing techniques, and developed their own power plants that had propelled Japanese naval aviation to dominance in the Pacific War's opening years. The Nakajima Sakae engine, powering the legendary Mitsubishi A6M0, had been a masterpiece of efficient design. 14 cylinders producing roughly 900 horsepower in its early variants, the Sakae represented Japanese engineering priorities perfectly. Lightweight construction, fuel efficiency, adequate power for air combat against what Japanese planners had anticipated would be inferior American fighters. Over 30,000 Sakae engines were manufactured during the war, making it one of the most successful Japanese power plants. Nakajima's more powerful designs followed similar philosophies. The Ha-41 and Ha-109 engines, used in bombers and heavier fighters, pushed output toward 1,100 horsepower. The Ha-115, powering the formidable Ki-84 Hayate fighter, reached 1,300 horsepower. These were respectable figures by mid-1930s standards, representing steady progression in Japanese engine development. But American engine development hadn't followed a steady progression. It had made quantum leaps that left Japanese capabilities struggling to catch up. When the R2800 double Wasp entered production in 1939, It was producing 2,000 horsepower from its initial production variants. By 1941, production models were rated at 2,100 horsepower. Late-war variants, incorporating water injection for emergency power, reached 2,400 horsepower in sustained military power ratings. With water methanol injection engaged, some variants briefly achieved 2,500 horsepower for takeoff and combat emergencies. These weren't experimental numbers. These were production ratings from engines manufactured by the tens of thousands. Pratt and Whitney built over 125,000 R2000, 800 engines between 1939 and 1960. Ford Motor Company manufactured them under license. Nash Kelvinator Corporation produced them. This was American mass production at its most sophisticated, cranking out engines that individual Japanese manufacturers would have struggled to build as one-off prototypes. The power gap was staggering. The most powerful production Japanese radial engine, the Nakajima Homare, powering late-war fighters like the Kawanishi N1K Shiden, produced roughly 1,800 horsepower. This represented the absolute peak of Japanese radial engine development, achieved only through enormous effort and requiring constant maintenance attention that frontline units could barely provide. Meanwhile, the R-2800 was producing 2,400 horsepower as a routine production specification in engines that proved remarkably reliable under combat conditions. But raw horsepower figures told only part of the story. The real revelations came when Japanese engineers began physically examining the captured Corsair engine in detail. The R-2800 measured 48 inches in diameter. Remarkably compact for such a powerful engine, this size efficiency came from design choices that Japanese manufacturers simply couldn't replicate with their industrial capabilities. The cylinder head cooling fins were the first shock. Standard practice in Japanese engine manufacturing involved casting or forging cooling fins as part of the cylinder head construction. This technique, proven and reliable, produced fins with adequate spacing for heat dissipation in engines producing up to 1,500 horsepower. But the R-2800's much higher power output generated heat that conventional cooling fin design couldn't handle. Pratt and Whitney's solution required a manufacturing capability that Japanese industry lacked. The R-2800's cooling fins weren't cast or forged. They were machined from solid metal using gang milling equipment that cut all fins simultaneously. The milling saws followed automatically guided paths that made the bottom of each groove rise and fall, creating fins whose roots followed the cylinder head's contour with extraordinary precision. The fins themselves were much thinner and more closely pitched than anything Japanese manufacturers could produce consistently in mass production. This wasn't just clever engineering. This was manufacturing sophistication that required machine tools, cutting instruments, and operator skill levels that Japan's wartime industrial base couldn't provide at scale. Japanese engineers examining these cooling fins understood immediately that replicating this manufacturing process would require retooling factories, developing new machine tools, and training workers in techniques their industry had never mastered. And all of this would need to happen while American bombers were systematically destroying Japan's industrial infrastructure. The crankcase construction revealed similar disparities. The R-2800 used a split crankcase design with exceptional dimensional accuracy. The tolerances, the surface finishes, the precision of the bearing surfaces all spoke to manufacturing capabilities that Japanese factories were struggling to achieve even in peacetime production, let alone under wartime pressures. Mitsubishi and Nakajima engineers had visited American factories in the 1920s and 30s. They had studied American manufacturing techniques. They knew, in theory, how these components should be made. But knowing the theory and possessing the industrial depth to implement it at mass production scale were fundamentally different challenges. The supercharger system demonstrated American advantages in metallurgy and precision manufacturing. The R-2800's two-stage supercharger, used in variants like the one powering the captured Corsair, required impeller blades manufactured to exacting specifications from specialized alloys. The tolerances on the impeller assembly, the bearing surfaces, the shaft alignment, All demanded manufacturing precision that Japanese industry could achieve in laboratory conditions, but couldn't sustain in production. Japanese engines used single-stage superchargers by necessity, not because Japanese engineers didn't understand the advantages of two-stage designs, but because their manufacturing capabilities couldn't produce the components reliably enough for mass production. When Japanese manufacturers attempted more sophisticated supercharger designs, the results were engines that required constant expert maintenance, suffered frequent failures, and never achieved their theoretical performance specifications under field conditions. The ignition system provided another revelation about American industrial maturity. The R-2800 used twin distributors and magnetos positioned prominently on the forward gear reduction housing. The distributor construction, the spark plug wire routing, the magneto design all reflected decades of American automotive industry experience applied to aircraft engines. These weren't experimental systems cobbled together by aviation specialists. These were refined, proven designs adapted from the millions of automobiles American manufacturers had been building since the 1920s. Japan had an automobile industry. Companies like Toyota and Nissan were producing vehicles for military and limited civilian use, but the scale was incomparable. American automobile production in 1941 alone exceeded 7 million units. Japan's entire automobile production from 1941 through 1945 totaled roughly 300,000 vehicles. This disparity in automotive manufacturing experience translated directly into aircraft engine capabilities. American engineers approached aircraft power plant design with an institutional knowledge base built from producing millions of reliable engines for civilian use. Japanese engineers were essentially starting from scratch every time they attempted to scale up production. The captured Corsair was transported to the Tsuchiura Aviation Technical Research Institute, the Imperial Japanese Army's primary facility for analyzing enemy equipment. The institute, located in the western suburbs of Tokyo, had examined captured American, British, and Soviet aircraft throughout the war. Their reports, meticulously detailed and brutally honest, had been warning senior military leadership about American industrial capabilities since 1943. When the R-2800 arrived at Tsuchiura, engineers began the systematic teardown that would reveal every aspect of the engine's design and construction. They photographed each component from multiple angles. They measured dimensions with precision instruments. They analyzed alloy compositions using spectroscopy equipment. They tested materials for strength, ductility, and fatigue resistance. They documented manufacturing techniques visible in the tool marks, surface finishes, and assembly methods. The teardown proceeded component by component, revealing new disparities with each system examined. The connecting rods showed sophisticated forging techniques. The piston rings demonstrated metallurgical capabilities Japan couldn't match. The valve train components, the camshaft mechanisms, the oil pump design, every element reinforced the same conclusion. The R-2800 represented an integrated system of advanced design and sophisticated manufacturing that Japanese industry, even at its pre-war peak capacity, would have struggled to replicate. But the most devastating realization came when engineers calculated the specific power output. The R-2800 was producing approximately 0.71 horsepower per cubic inch of displacement. When introduced in 1939, no other air-cooled engine in the world approached this figure. Even advanced liquid-cooled engines barely matched it. By 1945, with war emergency power ratings, some R-2800 variants briefly exceeded 1 horsepower per cubic inch. Japanese engineers understood that this specific power achievement wasn't just about design cleverness. It was about manufacturing quality, materials science, and the ability to maintain tight tolerances across thousands of components manufactured by multiple suppliers. It was about an industrial ecosystem that Japanese manufacturing, despite decades of development, simply didn't possess. The realization settling over the engineers at Tsuchiura was profound and profoundly disturbing. They weren't just examining an enemy engine. They were confronting evidence that the United States had achieved a level of manufacturing sophistication that Japan couldn't reach, couldn't replicate, and given the trajectory of the war, would never have the opportunity to develop. The R-2800 demonstrated that American aviation wasn't succeeding through individual technological breakthroughs. It was succeeding through industrial maturity, through decades of investment in manufacturing infrastructure, through a supplier network that could produce millions of precision components to exacting specifications, and through an engineering culture that prioritized practical reliability over theoretical performance. Japanese engines were designed by excellent engineers working within severe constraints. The Nakajima Homare, reaching 1,800 horsepower, represented a genuine achievement given Japan's industrial limitations. But it required expert maintenance. It suffered from frequent failures. It demanded constant attention from skilled technicians who were increasingly scarce as the war ground on. The R-2800, producing 33% more power, was famously reliable, easy to maintain, and designed to be serviced by ordinary mechanics with standard tools. This wasn't just an engineering gap, this was an industrial capability gap that exposed how fundamentally outmatched Japanese manufacturing had become. And sitting in a workshop at Tsuchiura, surrounded by the disassembled components of an American engine they couldn't replicate, Japanese engineers understood that no amount of pilot skill, tactical innovation, or fighting spirit could overcome this material disparity. The teardown process at Tsuchiura followed meticulous protocols developed over years of analyzing captured enemy equipment. Each component was photographed in situ before removal. Measurement data was recorded in duplicate. Material samples were prepared for spectroscopic analysis. The process wasn't rushed. Even in March 1945, with American carriers launching strikes against Japanese coastal cities and B-29 seconds reducing industrial centers to rubble, the engineers at Tsuchiura worked with the same careful precision they'd employed since the facility's establishment. The piston assemblies revealed manufacturing sophistication that Japanese engineers had anticipated but hoped might not be present throughout the entire engine. Each piston was machined from aluminum alloy forgings with dimensional tolerances measuring in thousandths of an inch. The piston ring grooves showed tool marks indicating precision grinding operations. The piston pins demonstrated heat treatment processes that gave them extraordinary strength without excessive weight. Japanese manufacturers could produce pistons of equivalent design. Nakajima and Mitsubishi had been building high-quality pistons for years, but the consistency, the precision across hundreds of thousands of units, the ability to maintain these tolerances in mass production while simultaneously manufacturing everything else a war economy required, this represented industrial depth Japan couldn't match. The valve train components told similar stories. The R-2800 used sodium-cooled exhaust valves in its cylinder heads, a sophisticated approach to managing the extreme temperatures generated by high-power combustion. The valves themselves were manufactured from specialized steel alloys. The valve seats were precisely machined and fitted. The valve springs showed consistent metallurgy across the entire engine, something Japanese manufacturers struggled to achieve when material quality varied between suppliers. Tsuchiura's metallurgists took samples from valve stems, cylinder heads, crankshaft journals, and connecting rod-bearing surfaces. The spectroscopic analysis revealed alloy compositions that matched nothing in Japanese industrial standards. Some elements were expected. Chrome, molybdenum, nickel, vanadium, all were common in quality steel alloys, but the specific combinations, the heat treatment protocols visible in the grain structure, the surface hardening techniques evident in bearing surfaces, all pointed to metallurgical sophistication that Japanese industry had never systematically developed. Oil system deserved particular attention because it revealed American design philosophy with unusual clarity. The R-2800's oil pump was substantially larger than theoretical minimum requirements would suggest. The oil passages through the crankcase were generously sized. The oil filtration system was robust to the point of seeming redundant. Japanese engines used more minimal oil systems, carefully calculated to provide adequate lubrication while minimizing weight and complexity. But the American approach, once again, prioritized reliability over theoretical efficiency. The oversized oil pump ensured adequate pressure even when oil viscosity changed with temperature. The large oil passages prevented blockages from affecting lubrication. The robust filtration kept contaminants from reaching bearing surfaces even under harsh field conditions. The system worked reliably for novice mechanics performing maintenance under combat conditions. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The fuel delivery system demonstrated similar over-engineering. The carburetor was a Bendix-Stromberg unit, substantially more sophisticated than Japanese carburetors, but also more reliable and easier to maintain. The fuel injection system, on variants equipped with it, represented engineering that Japanese manufacturers had explored but never successfully implemented in production engines. Japanese engineers examining these systems understood that each individual component could probably be replicated given enough time and resources. The crankshaft could be forged and machined by Japanese suppliers. The cylinder heads could be cast and finished in Japanese foundries. The connecting rods, the pistons, the valve train, all were within Japanese manufacturing capabilities at the level of individual components. But the R2800 wasn't just a collection of components. It was an integrated system where every element worked together, where manufacturing tolerances stacked without creating assembly problems, where parts from different suppliers fit together without extensive hand-fitting, and where the whole engine demonstrated reliability that emerged from thousands of careful design decisions rather than from any single breakthrough. This systematic approach to reliability, this engineering culture that assumed components would be manufactured by multiple suppliers and assembled by workers with varying skill levels, represented industrial maturity that couldn't be copied by studying a single engine. It had developed over decades in American automotive and aviation industries. It had been refined through millions of engines built, tested, failed, and improved. It was institutional knowledge embedded in engineering practices, manufacturing procedures, and quality control systems, rather than in any specific technical document. The comparison tables prepared by Tachikawa analysts laid out the disparities with brutal clarity: power output, specific fuel consumption, weight, dimensions, operating temperatures, maintenance intervals. Every metric told the same story. The R2800 was superior in some categories and competitive in all others, but its overwhelming advantage came from the combination of capabilities rather than from excellence in any single area. Japanese engines achieved competitive performance in specific metrics by accepting compromises elsewhere. The Nakajima Homare matched the R2800's power-to-weight ratio by running at higher temperatures with tighter tolerances and accepting much shorter maintenance intervals. The Mitsubishi Kase achieved respectable power output by accepting larger displacement and lower specific power. Every Japanese engine represented optimization within severe constraints. The R2800 appeared to operate without equivalent constraints. It produced high power without excessive weight. It ran at manageable temperatures without sacrificing performance. It achieved excellent specific fuel consumption without compromising reliability. It maintained consistent performance across altitude ranges without complex supercharger systems. The engine seemed to do everything well, and the reason became clear through the detailed analysis. American engineers had designed an engine assuming they would have adequate materials, sufficient manufacturing precision, and reliable component suppliers. Japanese engineers designed engines assuming they wouldn't have any of those advantages. The analysis of the captured R2800 wasn't complete, but the conclusions were already clear. American industrial power had created weapons that Japan simply couldn't match. And time, the one resource Japan desperately needed to close these gaps, had run out months ago. The technical reports generated by Tachikawa engineers in March 1945 made for grim reading at Imperial Japanese Army headquarters. The documents, stamped with appropriate security classifications and distributed to senior aviation officials, laid out in precise detail why replicating the R2800's capabilities was impossible given Japan's current industrial situation. But these reports went further. explaining why even if Japan had the manufacturing capabilities, the supply chain depth, and the time required, the fundamental approach to engine development had been flawed from the beginning. Japanese engine development had prioritized different values than American manufacturers. Weight savings dominated Japanese design philosophy. Every kilogram mattered in aircraft designed for extreme range and maneuverability. The Zero's legendary combat performance in the war's early years had vindicated this approach. Lightweight construction, minimal armor, engines designed for adequate power rather than overwhelming force. These choices had produced aircraft that dominated the skies over Pearl Harbor, the Philippines, and the Dutch East Indies. But this design philosophy had created engines that ran at the absolute limits of their materials' capabilities. Japanese radial engines typically operated at high RPM, extracting maximum power from relatively small displacements through aggressive supercharging and high compression ratios. This approach worked, but it left no margin for error, no reserve capacity for sustained high-power operation, and no tolerance for the manufacturing variations inevitable in wartime mass production. The R-2800, by contrast, was overbuilt by Japanese standards. American engineers had designed an engine with substantial safety margins. The cylinder construction was heavier than theoretically necessary. The crankshaft was beefier than pure performance calculations demanded. The connecting rods used more material than minimalist design would require. To Japanese eyes, examining the disassembled R-2800, these looked like inefficiencies, like wasted weight that degraded power-to-weight ratios. But these weren't inefficiencies. They were design margins that ensured reliability under combat conditions. They were insurance against manufacturing variations. They were allowances for pilot error, for maintenance performed by inexperienced mechanics under field conditions, for engines run beyond rated power in combat emergencies. The R-2800 didn't need to be babied. It could be abused and would keep running. Japanese engines couldn't survive that treatment. The Tachikawa analysis noted that American design philosophy seemed to assume that combat aircraft would be maintained by mechanics with automotive rather than aviation backgrounds, that pilots might inadvertently overstress engines during combat, and that field conditions would prevent the kind of careful, expert maintenance Japanese engines required. These assumptions, the report noted with barely concealed admiration, had proven entirely correct. The manufacturing depth supporting the R-2800's production revealed even more troubling disparities. Pratt and Whitney didn't manufacture everything in-house. The company relied on an extensive supplier network for castings, forgings, precision, machined components, and specialized assemblies. But this wasn't a weakness. This was industrial maturity that Japanese manufacturers couldn't match. American suppliers could produce cylinder heads, crankshafts, connecting rods, and thousands of other components to specifications so precise that they could be assembled into finished engines with minimal hand-fitting. Japanese manufacturing required extensive hand-fitting and custom adjustment of components during assembly. This wasn't because Japanese manufacturers preferred handwork. It was because their machine tools, their inspection equipment, and their supplier quality control couldn't achieve American precision levels consistently. The reports from Mitsubishi and Nakajima engineers who examined the captured components told similar stories. Mitsubishi's Nagoya Engine Works, one of Japan's most sophisticated power plant facilities, had been attempting to develop engines exceeding 2,000 horsepower since the late 1930s. The Mitsubishi Mk9, also known as the Ha 43 inches Army nomenclature, was designed to produce 2,200 horsepower from 18 cylinders arranged in 2 rows. The Ha 43 had everything Japanese engineers could provide: advanced design, sophisticated supercharging, high-quality materials from Japan's dwindling strategic reserves, expert manufacturing by Mitsubishi's most skilled workers. The engine ran on test stands. It achieved its rated power under carefully controlled conditions, but it never entered mass production. The engine required too much expert attention. Manufacturing tolerances were too tight for reliable reproduction across multiple production lines. The failure rate was unacceptable, and by 1944, when these problems became undeniable, Japan no longer had the time, resources, or industrial capacity to solve them. The Nakajima Homare, Japan's most powerful production radial, illustrated the same limitations from a different angle. The Homare had reached production, powering several late-war fighters. On paper, its specifications looked competitive. 18 cylinders, 1,800 horsepower, reasonable specific fuel consumption, but in service, the Homare was notorious for unreliability, cylinder head cracking, valve train failures, overheating during prolonged high-power operation, maintenance requirements that frontline units couldn't meet. Japanese pilots developed bitter jokes about Homare-powered aircraft. Praise it in the morning, curse it in the afternoon, referring to the engine's tendency to run acceptably during morning flights, but overheat and fail during afternoon operations. Mechanics learned to expect failures, to stockpile spare parts they couldn't reliably obtain, and to perform extensive pre-flight inspections that American mechanics would have considered paranoid. The R-2800, producing 2,400 horsepower under similar operational conditions, had no equivalent reputation. American pilots trusted their Corsairs, their Thunderbolts, and their Hellcats to bring them home through battle damage, mechanical stress, and extended combat operations. The engines worked. They were reliable enough that pilots could focus on fighting rather than nursing temperamental power plants. This reliability gap translated directly into operational effectiveness. Japanese fighter units in 1945 were lucky to maintain 50% aircraft availability on any given day. Mechanical failures grounded aircraft as often as battle damage. American units routinely maintained 80% availability or higher. This meant that American squadrons could generate more sorties with fewer aircraft, could replace losses more rapidly, and could sustain operational tempo that Japanese units couldn't match. The strategic implications were devastating. Japan had entered the Pacific War with excellent aircraft powered by engines adequate for the anticipated conflict. But American aviation had evolved faster than Japanese industry could respond. By 1943, the gap was noticeable. By 1944, it was substantial. By 1945, examining a captured R-2800, Japanese engineers understood the gap had become unbridgeable. The metallurgical analysis of R-2800 components revealed another dimension of American advantage. The aluminum alloys used in cylinder heads, pistons, and crankcase castings showed composition and heat treatment that Japanese manufacturers couldn't consistently replicate. The steel alloys in crankshafts, connecting rods, and valve train components demonstrated similar sophistication. These weren't exotic materials requiring rare strategic resources. These were industrial alloys that American manufacturers had developed for automotive and aerospace applications over decades. Japan had skilled metallurgists. Japanese universities produced excellent materials scientists. Japanese steel quality was generally excellent, particularly in specialized applications like sword-grade steel and naval armor plate. But the specific alloys and heat treatments required for high-performance aircraft engines demanded infrastructure and expertise Japan had never developed at industrial scale. American materials science had been refined through millions of automotive engines, thousands of aviation power plants, and decades of industrial competition, where manufacturers learned from failures and continuously improved their processes. The aluminum alloys particularly highlighted these differences. American manufacturers used sophisticated casting processes that produced cylinder heads with consistent density, minimal porosity, and predictable material properties. The heat treatment protocols, visible in the grain structure under microscopic examination, showed precisely controlled heating and cooling cycles that gave the aluminum optimal strength characteristics. Japanese aluminum casting technology lagged behind American practices by perhaps a decade. Japanese foundries could produce acceptable castings for aviation use, but consistency varied between batches. Porosity was a persistent problem. Heat treatment was less precise. The result was components that worked adequately, but required more frequent inspection, more conservative operating limits, and more extensive quality control during manufacturing. The steel forgings told similar stories. The R2800's crankshaft showed forging techniques that produced optimal grain flow through the complex shapes. The connecting rods demonstrated similar sophistication. American forging presses, dies, and heat treatment facilities represented capital investments that Japanese manufacturers couldn't match even before the war began, restricting resource availability. One particular detail caught Tsuchiura engineers' attention. The R2800's connecting rod bearing shells used a three-layer design. Steel backing provided structural support. A copper lead alloy middle layer provided the bearing surface. A thin overlay of tin-based material provided additional protection during startup and abnormal operating conditions. This sophisticated construction required specialized manufacturing equipment and precise control of plating processes. Japanese manufacturers used simpler two-layer bearings that worked adequately under ideal conditions, but wore faster and had less tolerance for contamination or marginal lubrication. The three-layer American design represented insurance against field conditions, protection for situations where maintenance might be delayed or oil quality might be compromised. Once again, American engineers had assumed things would go wrong and designed accordingly. Japanese engineers had assumed proper maintenance and designed to minimum specifications. The bearing materials illustrated this perfectly. The R2800 used specialized bearing alloys that could sustain high loads at elevated temperatures with minimal wear. Japanese manufacturers had equivalent materials for critical applications, but couldn't produce them in the quantities required for mass engine production. This forced compromises. Japanese engines used less sophisticated bearings that required more frequent replacement, more careful maintenance, and couldn't tolerate the abuse American bearings handled routinely. The supercharger impellers provided another revealing comparison. The R2800's two-stage supercharger used impellers manufactured from aluminum alloys with precisely controlled blade profiles. The machining tolerances on these impellers, measured in thousandths of an inch, required specialized equipment and highly skilled operators. The blade surfaces showed careful finishing that minimized turbulence and maximized compression efficiency. Japanese single-stage superchargers used simpler impeller designs, partly because Japanese manufacturers couldn't reliably produce the more sophisticated shapes. The machining precision wasn't consistently available, the alloys weren't as well controlled, the finishing processes weren't as refined. Each limitation seemed small in isolation, but together they resulted in superchargers that were 15 to 20% less efficient than American equivalents. The gear reduction systems demonstrated American advantages in another critical area. The R2800 used precise gear cutting that produced quiet, efficient power transmission from the engine to the propeller. The gear teeth showed consistent profiles, proper surface hardening, and careful finishing. Japanese gear cutting technology produced acceptable gears, but the precision and consistency didn't match American standards. Japanese engines often had noisier, less efficient gear systems that required more frequent inspection and maintenance. The ignition timing mechanisms revealed similar disparities in manufacturing precision. American distributors used components manufactured to tolerances that ensured consistent spark timing across all 18 cylinders. Japanese distributors, working with less precise components, required more frequent adjustment to maintain optimal timing. Pilots and mechanics often joked grimly that American engines ran smoothly from the factory, while Japanese engines required expert tuning to run properly at all. These accumulated small advantages, none decisive individually, combined to create the reliability gap that separated American and Japanese aviation. An American engine with properly functioning oil system, precisely timed ignition, well-manufactured bearings, and efficient supercharger could run for hundreds of hours with routine maintenance. A Japanese engine, optimized around less capable manufacturing, required expert attention after every mission to maintain combat effectiveness. One of the Tsuchiura reports included a particularly sobering calculation. Given Japan's current manufacturing capabilities, current material availability, and current industrial infrastructure, replicating the R2800's power output would require an engine roughly 20% larger in displacement, running at higher operating temperatures, requiring more sophisticated metallurgy than Japan could provide, and demanding maintenance intervals Japanese logistics couldn't support. And even then, reliability would be questionable. The calculation wasn't speculative. Engineers had attempted similar designs. The Nakajima Homare represented Japan's most ambitious attempt to match American power levels: 18 cylinders, sophisticated design, best materials available, expert manufacturing by Nakajima's most skilled workers. The result produced 1,800 horsepower on test stands, but reliability and field service was poor enough that some units preferred older, less powerful but more reliable engines. The conclusion was inescapable. Japan couldn't build an R-2800 equivalent, not in 1945. Not even if the war magically paused to give Japanese industry time to retool. The capability gap wasn't just about current wartime conditions. It reflected decades of accumulated industrial development that Japan had never pursued because the need hadn't been apparent until American manufacturing demonstrated what was possible. By April 1945, the captured Corsair engine had become something of a pilgrimage site for Japanese aviation officials who could arrange visits to Tsuchiura. Senior officers came to see physical evidence of American industrial power. Engineers came hoping to find something, anything, they could learn and apply to Japanese production. What they found instead was confirmation of what many had suspected since mid-1944. The war was lost, not because Japanese pilots lacked skill or courage, not because Japanese tactics were inferior, but because American industry had created weapons in such quantities and quality that Japanese forces simply couldn't match them. The specific example of the R-2800 carried particular weight because engines were fundamental to aviation performance in ways that other systems weren't. Better armor could be added to aircraft, weapons could be upgraded, tactics could evolve, but if the enemy's engines produced 33% more power than yours, if their engines were more reliable, if they could manufacture engines faster than you could destroy them, then no amount of pilot skill could bridge that gap. The final Tsuchiura report, submitted in May 1945, included a section that would have been unthinkable earlier in the war. It explicitly stated that Japanese aviation industry had been pursuing the wrong development priorities since the mid-1930s. The emphasis on lightweight construction, on minimal airframe weight, on extreme range at the expense of armor and firepower. All of these had been mistakes based on incorrect assumptions about the coming conflict. American aviation development, the report argued, had correctly anticipated a war where industrial capacity would matter more than individual aircraft performance, where pilot survival would matter more than aircraft weight, where reliability would trump theoretical maximum performance, where engines that worked consistently would beat engines that performed brilliantly under ideal conditions but failed under stress. The Americans had been right. The Japanese had been wrong, and by May 1945, with American bombers reducing Japanese cities to ash and American fighters achieving total air superiority, that mistake was costing Japan everything. The B-29 raids accelerated through spring 1945, and Japanese interceptors struggled to reach the bombers' operating altitudes with enough power remaining to conduct effective attacks. American fighters, powered by engines like the R-2800, could climb rapidly, fight at high altitude, and return to base with power reserves Japanese engines couldn't match. The operational advantage was crushing and getting worse as American industry continued improving their engines while Japanese manufacturing capacity collapsed under sustained bombardment. Tsuchiura itself was bombed on April 19, 1945. The raid damaged several buildings and destroyed some equipment, but the captured Corsair and its disassembled R-2800 survived. Engineers continued their analysis even as American aircraft attacked the facility studying American technology. The irony wasn't lost on anyone involved. The last substantive report on the R-2800 was dated August 7, 1945, 1 day before Soviet forces invaded Manchuria, 8 days before Emperor Hirohito's surrender broadcast. The report concluded that the Pratt and Whitney R-2800 represented the pinnacle of practical piston engine design for aviation applications. that its combination of power, reliability, manufacturability, and operational flexibility made it the standard against which all other engines should be measured. And that Japanese industry would require decades of peacetime development to achieve equivalent capabilities. That final assessment proved prophetic. Japan's aviation industry was dismantled after surrender. Nakajima dissolved into multiple companies, eventually becoming Subaru. Mitsubishi Heavy Industries survived but was prohibited from aircraft production until the early 1950s. When Japanese aviation industry finally resumed, it did so by licensing American designs, studying American manufacturing techniques, and essentially starting over with the accumulated knowledge that American industry had developed over decades. The captured Corsair disappeared from Tachikawa sometime in the chaos of Japan's surrender. Some reports suggest American occupation forces recovered it. Others indicate it was scrapped for materials in the desperate final months of the war. The R-2800 that had traveled from an American factory to a rice paddy near Tokyo to a Japanese research facility left no confirmed final location in historical records, but the lessons it taught endured. The F-4U Corsair went on to serve in Korea, proving that piston-powered fighters remained viable even against early jets in certain roles. The R-2800 powered civilian airliners through the 1950s, accumulating millions of flight hours and establishing reliability records that jet engines would eventually match, but never definitively exceed in their role. Over 125,000 R-2800 engines were manufactured, and hundreds remain operational today in vintage aircraft. Still running, still reliable, still demonstrating the industrial maturity that made them possible. For Japanese engineers examining that captured engine in early 1945, the R-2800 represented something more profound than just superior American technology. It was physical evidence of industrial ecosystems that Japan had never developed, manufacturing depth that couldn't be improvised, under wartime pressure, and accumulated expertise that came only from decades of investment in infrastructure, worker training, and supplier development. The Zero had been a brilliant achievement of Japanese engineering, optimized for the constraints within which Japanese designers operated. The R-2800 was a brilliant achievement of American industrial maturity, possible only because American manufacturers had those constraints. Two different approaches to aviation, two different philosophies about what mattered in modern warfare. By 1945, one philosophy had proven decisively superior. The 2,250 horsepower that American factories routinely coaxed from the R-2800's 18 cylinders represented more than just thermodynamic efficiency and mechanical engineering. It represented an industrial civilization that could design for mass production, manufacture to exacting tolerances, supply components from thousands of specialized vendors, and do all of this while simultaneously producing every other weapon system a modern military required. Japan had fought brilliantly with the tools its industry could provide, but those tools, exemplified by engines producing 1,300 to 1,800 horsepower through heroic engineering effort, weren't enough when the enemy showed up with 2,400 horsepower engines, produced by the tens of thousands with industrial ease. The engineers studying that captured engine understood this completely. They'd understood it, in fact, probably since sometime in mid-1944. But understanding didn't change reality. It just made the inevitable defeat easier to explain. The R-2800 sitting, disassembled at Tachikawa in spring 1945, wasn't just an enemy engine. It was a verdict on Japanese industrial development, a verdict that Japanese aviation couldn't appeal, couldn't overturn, and ultimately had to accept as American forces prepared to invade the home islands with aircraft powered by engines Japan would never match. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.